Okay, so we would like to compute a triple integral, which is over a part of the unit pole in that resides in one octant, that lies in one octant. And this octant is defined by the condition z is less than or equal to 0, x is greater than or equal to 0, and y is less than or equal to 0. So our first order of business is to try to express this domain in terms of spherical coordinates. So we will have all the rho thetas and phis. First of all, rho is very simple. It's between 0 and 1. And uh, phi is very simple too, because we are in negative z territory. So if we were to sketch the, let's say, yz plane, then we are exactly here. And this implies that phi is between pi over 2 and pi. And finally, for theta, if we draw the xy plane, then we see that we are in this territory right here, which means that theta will be between 3 pi over 2 and 2 pi. We could also put negative pi over 2 and 0. It's pretty much the same thing. So now that we have the domain, we should be able to do everything else in a straightforward way. So let's begin by putting together the integral. So we will have from 0 to 1 d rho, from 3 pi over 2 to 2 pi d theta, and from pi over 2 to pi d phi. Okay, now the integrand is z, and z happens to be rho cosine phi. And finally, the Jacobian is rho squared sine phi. Okay, so here we have a situation where the integrand is the product of three quantities, one in rho, one in phi, one in theta. The one in theta can be taken to simply be the function 1, and all the endpoints are constant. It's good to know that in such a case, the integral splits as the product of three integrals, one in rho, one in theta, one in phi, with the corresponding limits, which are constant as I emphasized, and the corresponding function. So this will be rho cubed d rho times 3 pi over 2 to 2 pi d theta times pi over 2 to pi cosine phi sine phi d phi. Okay, now it should be pretty straightforward to work these integrals out. So this one, for example, the antiderivative is rho to the fourth over 4, so it's very easy to see that it's 1/4. The middle one is pi over 2. It's simply the length of the interval over which we integrate. And finally, for the last one, we would have to do a substitution. U is equal to sine phi, du is equal to cosine phi d phi, which means that this integral is going to be u du, but we have to be careful from what to what. So we have to take pi over 2, plug it into sine phi, and that will give us 1 for the lower endpoint, and also take pi, plug it into sine phi, that will give us 0 for the upper endpoint, which will give us, of course, negative 1/2, because if it was the other way around, it would have been 1/2. So if we put everything together, then we will get negative pi over 16. And sometimes at this point, I get the question, why do we find negative pi over 16? Isn't that are we supposed to get a positive number because we're computing volume? Well, remember, we're computing signed volume, and in this case, it's the volume of a four-dimensional or a region in four-dimensional space. And if you take a look at the integrand is in negative territory. So that means that in four-dimensional space, that region would be located below the three-dimensional plane, hyperplane, as we might call it. So it makes perfect sense that what we find is a negative number, especially since the integrand is a negative function. So that should not concern us. And that's all. Thanks for watching.